Welcome to the Merlin and Metro News Network. Today's program covers the pressurization system. Now, this system often intimidates mechanics much the same way electrical circuits do. Now, this is because the pressurization control system uses vacuum as a controlling pressure. And of course, like electricity, you can't see, feel, or even hear vacuum pressure. Unlike a hydraulic system, vacuum can be leaking from every connection in the system and you'll never know it. On the positive side, the pressurization system rarely fails, and so most mechanics don't have to perform much maintenance on the system. Probably the number one and most important maintenance activity is cleaning of filters used in the system. And now let's roll our first program.
The pressurization system is used to increase passenger comfort. Were it not for pressurization of the cabin, many passengers would experience ear discomfort or ear popping as the aircraft changes altitude. This is due to the fact that pressures within the human ear cannot change quickly enough in responses to changes in aircraft altitude. Research in the 1960s indicated that many passengers avoided flying on commuter aircraft simply because the majority were unpressurized. The pressurization system is used to maintain a constant pressure level within the cabin for increased safety and comfort. Since the air conditioning system provides abundant air into the cabin, the pressurization system works by controlling the rate at which that air is allowed to escape from the cabin. On the Merlin and Metro aircraft, the system consists of a cabin pressurization controller located in the instrument panel, an outflow valve located on the aft pressure bulkhead, a safety valve located on the forward pressure bulkhead, a pneumatic relay located in the tail cone area, a manual rate control and auto manual selector located on the pilot's side console, and ambient pressure vents located on the nose exterior section, inside of the nose baggage compartment, and aft tail cone area. The system also senses cabin pressure through filter assemblies and connects to the aircraft vacuum system in several places. Engine bleed air, after being conditioned, is introduced into the aircraft cabin through the heating and cooling systems. Unless both flow control valves are closed, this air supply will be present anytime one or both engines are operating. The pressurization system will regulate the outflow of this air from the aircraft cabin through a valve located on the aft pressure bulkhead. The system regulates this outflow to achieve two purposes. First, the structure of the aircraft can only withstand a certain amount of pressure within the cabin. Second, the rate at which the pressure within the cabin changes must be regulated for passenger comfort. As the aircraft ascends in altitude, the ambient pressure outside the aircraft decreases. The pressurization system will sense this and begin allowing less and less air to escape from the aircraft, thus raising the difference between cabin pressure and the ambient pressure. To the passengers on board, this seems as though the pressure is remaining constant. As the aircraft continues to climb, the ambient pressure continues to decrease, and the pressurization system will continue to restrict the flow of air from the aircraft. As this process continues, the pressure within the aircraft is becoming greater than the external or ambient pressure. This means that the pressure inside of the aircraft is now pushing out on the structure of the fuselage. The structural limit of the aircraft is reached at 7 psi. This means that the most the pressure within the cabin can ever exceed the ambient pressure is 7 psi. On a typical day, this pressure differential will be reached at about 16,800 feet. Once this pressure differential has been reached, the pressurization system will have to begin reducing the cabin pressure, even if the aircraft continues climbing. Under no circumstances can the pressurization system allow the pressure within the cabin to exceed the ambient pressure by more than 7 psi. The amount of air that is allowed to escape from the cabin is controlled by the outflow valve. This is a round, spring-loaded, poppet-type valve. It is pneumatically operated by applying vacuum to the valve through this line. The greater the vacuum applied, the farther the valve will open. The source of this controlling pressure is a pressurization controller located in the instrument panel. The controller senses ambient pressure, cabin pressure, and the position of pilot-operated controls on the front of the unit. From this information, it will issue the appropriate vacuum signal to properly position the outflow valve. The controller actually sends these signals to a device called a pneumatic relay, and it, in turn, issues signals to the outflow valve. The pneumatic relay should not be confused with an electrical relay in function. If the pneumatic relay were considered in electrical terms, it would be called an amplifier. An electrical relay is usually simply on or off, while an amplifier produces an output signal that is stronger but otherwise identical to the input. The pneumatic relay receives a relatively small vacuum signal from the controller and produces an identical but considerably stronger signal to send to the outflow valve. Because of the length of plumbing between the cockpit and the outflow valve, the signal sent to the outflow valve from the controller would produce sluggish results. The pneumatic relay boosts or relays the controller signals to the outflow valve so that the reaction will be quick and positive.
The pressurization system is not written up very often, but when it is, problems often result. One of the most problematic areas is the language pilots speak versus what we mechanics understand. In the case of the pressurization system, controls and indicators are often marked in terms of pressure. But there are two kinds of pressure being discussed. First off, there is pressure altitude, which relates to the pressure at a given altitude. The second pressure is absolute, which is measured in psi. Now, since the location of this studio is only a few hundred feet above sea level, we can assume that our pressure altitude is sea level. In absolute pressure, it's about 14 psi. Now, if we took off from here and began climbing, our pressure altitude would increase. But we know that the absolute pressure goes down as altitude increases. That's what makes our ears pop while driving through mountainous areas. So when we have a pressure altitude of, say, 16,000 feet, the absolute pressure is actually less, probably around 7 psi. The pressurization system will make up this difference by pumping as much as an additional 7 psi of air into the cabin, so that at 16,000 feet, the pressure inside the cabin will still be about 14 psi absolute. If this increased pressure is pumped into the cabin at a rate that closely matches the aircraft's rate of climb, the passengers aboard the aircraft won't notice any pressure difference. A typical example of how these differences cause problems is the write-up, cabin rate of climb is too high. Now what this means is that the pressure inside the cabin is not being increased fast enough to compensate for the decreasing ambient pressure, and the passengers' ears are popping. Another way of saying the same thing is that the pressure altitude at which the cabin is operating is increasing too quickly. Since an increase in pressure altitude means that the absolute pressure is decreasing, the English translation of this write-up is, the cabin isn't pressurizing fast enough. Before beginning maintenance on the pressurization system, make sure you and the pilot understand each other, and you are actually working on the real problem. Now let's return for the conclusion of our program.
Now that the pressurization controller has responsive control over the outflow valve, The next major consideration is how does a controller know when to open or close the valve? Within the controller is a bellows and two pressure diaphragms. Since the mechanic cannot disassemble and repair the controller in the field, we're going to take some liberties in describing its internal workings. Let's start with a device called an isobaric bellows. Despite this impressive sounding name, it is nothing more than a sealed bellows. Since it is sealed, its length will be a function of the surrounding pressure. If the surrounding pressure is greater than that inside the bellows will begin to collapse. If the surrounding pressure is less than the pressure in the bellows will begin to expand. One side of the bellows is attached to the housing of the controller. It incorporates a calibration adjustment that is used during setup at the factory. The other side of the bellows is attached to a pivoting arm. As the bellows changes length, this arm will move back and forth. The end of the arm is connected to a spring that can have its tension adjusted by a rotatable knob on the front of the controller. As this knob is rotated, it will increase or decrease tension on the spring, which will in turn increase or decrease the working length of the bellows. You can think of the spring as a means of adjusting the at-rest length of the bellows. The bellows and pivoting arm are connected to another type of spring that is in turn connected to a rubber diaphragm that extends across the controller. The other side of the rubber diaphragm contacts a spring-loaded metering valve. This valve is what controls the amount of vacuum that enters from the aircraft's vacuum system. Remember that it is the amount of vacuum supplied to the outflow valve that determines how far it will open. Clearly, the movement of the metering valve will then be able to control the opening and closing of the outflow valve. Now all we have to do is explain how the metering valve is controlled. Earlier, we said that a rubber diaphragm extended across the controller, thus separating the controller into two major chambers. One side we call the reference chamber. The other side is the rate chamber. As we begin our flight, the pressure in the two chambers is equal. The balance between the bellows and the rate control spring and the metering valve spring will be such the metering valve will be opened. Since it is open, there will be vacuum applied to the outflow valve, and therefore it will be open. As the aircraft ascends, the ambient pressure and the cabin pressure will begin decreasing. Since cabin pressure is connected to the reference chamber and not to the rate chamber, the pressure difference will begin to push the diaphragm towards the reference chamber. This will close the metering valve somewhat, which in turn will reduce the vacuum applied to the outflow valve and cause the valve to begin closing. This in turn will increase the cabin pressure, which will increase the pressure in the reference chamber. This will cause the diaphragm to be pushed back towards its before flight position and open the metering valve. Even though we now have a means of maintaining the pressure in the cabin equal to that at takeoff, there are still some rough spots. For instance, we have no way to control the rate at which the controller adjusts the cabin pressure. This is accomplished by a rate control knob. This knob will adjust a rate metering valve that controls the introduction of a small amount of cabin pressure into the rate chamber. This then is used to control how fast the cabin rate of pressurization changes. Because the control does not close off fully, the minimum rate of change is approximately 50 feet per minute, while with the control fully open, the rate is approximately 2,000 feet per minute. The rate control also affects passenger comfort when the pilot adjusts the other knob on the controller. We said earlier that this knob controlled the tension of the spring that interacts with the bellows. What this spring really does is allow the pilot to compensate for different elevation takeoff and landing fields. If, say, after taking off from a near sea level field, the pilot wants to adjust the controller for landing at a high altitude field. This could result in a sudden pressure change that would be uncomfortable for the passengers. The rate control will, however, limit the rate at which this change takes place, in accordance with the pilot's setting. One thing you may have noticed by now is that there is no connection to the ambient pressure outside the aircraft. One of the duties of the pressurization system is to ensure that the maximum differential pressure between cabin and ambient pressure outside the aircraft is not allowed to exceed 7 psi. To accomplish this, another diaphragm and metering valve are installed. Called the differential metering valve and differential diaphragm, these two units are located in a separate chamber within the controller. The diaphragm separates this chamber into two smaller chambers. A spring tends to push the metering valve to the closed position. One side of this diaphragm is connected to the reference chamber. The other side of the diaphragm is connected to the ambient pressure through two static ports installed in the nose of the aircraft. As the aircraft climbs, the ambient pressure outside the aircraft becomes less. If everything is working properly with the pressurization system, the cabin pressure should remain constant. Consequently, the diaphragm will be deflected against the spring that is holding the metering valve closed. The force exerted by this spring has been carefully calibrated and adjusted so that it requires a 7-pound difference across the diaphragm to cause it to compress. As it does, it allows the metering valve to open, which causes some of the pressure in the reference chamber to be dumped overboard. This will, in turn, cause the vacuum pressure to the outflow valve to be increased, which causes the valve to open slightly and decrease cabin pressure. In this fashion, the cabin pressure differential will never be allowed to exceed 7 psi. The outflow valve and the cabin safety dump valve also play an important role in making sure the 7 psi differential is not exceeded. Each valve is connected to ambient pressure and cabin pressure. Each incorporates a differential pressure sensing valve that will open if 7 psi is exceeded. The outflow valve is normally set to open at 7.15 psi, while the dump valve is set to open at 7.3. Both valves also sense negative pressure in the cabin as well. If for any reason the pressure inside the cabin is ever less than the ambient pressure outside the cabin, the valves will open to equalize the pressures. There is also a provision to provide the pilot with manual control over the outflow valve for emergency purposes. A two-position cabin pressurization selector valve allows vacuum to be routed to either the controller for automatic operation or to a manual position, which will route vacuum to a manual rate control. The rate control is a manually adjustable metering valve. Its effect is very coarse, but ultimately can accomplish the same thing as a controller without the refined features. As it's moved counterclockwise towards the decrease position, it will apply more and more vacuum to the outflow valve, causing it to open farther. Likewise, when the knob is rotated away from the decrease position, less vacuum is applied to the outflow valve, which results in increased cabin pressure. When operating in this mode, the built-in maximum differential pressure regulator of the outflow valve and safety valve limit the differential between internal pressure and external pressure to 7 psi. The use of the manual control has no effect, however, on the safety features installed in either the outflow or dump valve. Their respective maximum pressure differential assemblies will still open the valve when the maximum pressure differential is reached, regardless of the manual rate setting. Another facet of the system is the need for a smooth transition from totally ambient conditions, such as when the aircraft is parked or taxiing, to the condition whereby the cabin pressure is being controlled by the pressurization system. This transition usually occurs at takeoff and can be a source of cabin pressure bumps as the pressurization system takes over. To prevent these bumps, vacuum is connected to the dump valve located on the forward pressure bulkhead. Remember, this valve is being electrically commanded to the open position anytime the weight is on the gear. At rotation, this electrical signal is lost and the valve will close. But because of the vacuum connection to the valve, it will close slowly. This slow closure allows the pressure within the cabin to smoothly transition to the control of the pressurization system.
That concludes our discussion of the pressurization system. Despite the problems of dealing with a system driven by vacuum, the pressurization system should not cause you much trouble if you remember to always make sure you completely understand the write-up before beginning to work. Until our next program, good flying and good maintenance.